So, in this video, we are going to look at simple harmonic motion, kinematics and energy when the relationship is with respect to position. Okay, and I'm going to call the position as x. All right, so all the equations that I will derive in this particular video will be in terms of x. So we want to ask questions like, I have a pendulum here and it's going to swing back and forth. What is the speed at a certain distance x measured from equilibrium position? So here to here is x. Wanna, know what is the speed of the massive bob here? What is the acceleration of the massive bob here? Okay, so I'm going to write here, what is V and what is A of this bob. All right, so imagine the pendulum swinging back and forth. Go and swing a pendulum, go and stare at it. So I want to find V in terms of x and A in terms of x. And some of you may be thinking, teacher, I know how simple harmonic motion got a definition equation one. And the definition equation says that the acceleration is equal to negative omega square x. Don't I already have one of the equation? And if you're thinking like that, well done. Yes, we definitely have one of the equations already. That would be the acceleration against, so I'm going to write here, acceleration A, the unit will be meter per second square, against displacement x, unit here, meter. All right, so we remember that the defining equation is A is equal to negative omega square x. So you should get a straight line passing through the origin that looks something like this. Straight line passing through the origin. Okay, so level 1 question will be, how do you know it's in simple harmonic motion? If the relationship between acceleration and displacement is as projected in front of me. But a few important points. If I zoom out and you look at the pendulum, the pendulum swinging here to here, so this part here is the amplitude, the maximum possible position of the pendulum. So I'm going to call this A, but sometimes, and certain books may call it x naught. Okay, and this will be my negative A. It's the amplitude, okay? And you may be wondering, teacher, what is this value? This maximum value, and what is this negative value? What this? Well, you can always substitute into this equation here. So how can we substitute? Well, you can say let x will be equal to A. So from here, A will be equal to negative omega square amplitude. Okay, so don't confuse lowercase a and uppercase A. Uppercase A is amplitude and lowercase a is acceleration. So I'll write here for you. A is amplitude. Okay, amplitude of the system. Okay, so here will be negative omega square A. And if you repeat the process again, I'm just going to call it A omega square. You repeat the process again, up here will be A omega square. Okay, because when you let x be negative A, you put negative A into this equation, then your A will be negative becomes positive, omega square A. All right, pretty cool stuff. So make sure you know this. Okay, you know the peak values. And of course, if let's say you are asked to find the gradient of the graph, gradient of this graph is equal to negative omega square. So sometimes they will give you a straight line and they'll ask you to find stuff like, oh, what's the frequency or what is the period? Well, gradient is negative omega square and omega is 2 pi f or 2 pi over t. Pretty straightforward. This is not a new graph. Part 2. We have acceleration against displacement. Now what about the velocity? Velocity v against displacement x in meter. What do you think? Okay, so before we draw this graph, okay, there are two ways to go about doing this. One, you could look carefully at the oscillation of a pendulum and deduce the speed of the graph. So one route we can go by intuition and just observation. On the other route, if let's say you have enough mathematical ambition, you can actually try to derive the equation. Okay, so I will be talking about the first way, which is the intuition way, and show the equation. The derivation will be in a further physics video. Right, so I zoom out a bit already, so you can do the, let's look at or observe a oscillating pendulum thing. So think of a pendulum that's oscillating. Hopefully you know by now, as the pendulum is on the way up, it will slow down. Why? Gain GPE lo. Go higher ma. GPE higher, 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 higher. Bloop. GPE maximum. So when GPE is maximum, we know at the highest position the speed is 0. Okay, so let me write for you. Okay, here, this point here, when the x is equal to amplitude, okay, so this one is A, velocity is 0. Because it's 0 ma. Teacher, opposite direction also same, right? Yeah lah, because what will happen to the pendulum bob when it's swinging up in the opposite? Because the pendulum is going to go tick, tock, not the app. Tick, tock, tick, tock. So when it's on the way up, it would lose KE, gain GPE, and then here, stop. All right, so at this point, you can just mark a point here and say, you know, when x is equal to negative A, V is also equal to 0. Wow, I got 2 plots now. My maths teacher tell me if I have 2 plots, I have a confident graph. Okay, now what about the equilibrium position? And you may be thinking, oh teacher, I know. Equilibrium position is when it's at the fastest, right? So here, at this point, x is equal to 0. Velocity is maximum. Ooh. Okay, so maximum means big lah, right? So here, positive. A. So the graph just join this one? Well, yes, but there's a scenario here where the pendulum could be moving to the right. Okay, so let's say I follow the regular old sign convention. I put right to be positive and left to be negative. Okay, so when the pendulum is on the way up, okay, on the way, so let's say the pendulum is on the way up. So how do I draw this? Maybe the pendulum is, when the speed is in this direction, V, this is positive. Okay, so this is V maximum. And of course, the pendulum sometimes, is on the way to the right upwards. But sometimes the pendulum could be moving to the left, right? Okay, so when the pendulum is moving to the left, let me swap colors here. If the pendulum is moving to the left, like that, in this direction, this would be negative V. So sometimes it could be negative V max because the pendulum goes tick, tock, tick, tock, okay? Goes back and forth, 2 direction, need positive, negative. Okay lah, you got 4 points. Big brain time. How are you going to join them together? Teacher, I can draw a square shape, you know, like the rhombus kite. No. Okay, if you think about the velocity and motion, you cannot have sharp edges, so you need to join them in a smooth curve. So I guess the only way to join them in a smooth curve is to draw something that's a little bit circular and elliptical. Maybe something like these. Okay, of course, I'm sure you can draw a nicer one. Or you could Photoshop the graph like me. No lah, joking. Okay, so you get something like that. So a few things about the graph. You will notice that except when the value of x is at the maximum points, all different values of x will have 2 v's. Okay, so for example, when x is at 0 here, you can have positive Vmax or negative Vmax. When x is at maybe, I don't know, let's put, where should I put? Let's say here. Let's say x is here, middle at the midpoint. Okay, you will have 2 values of V. Okay, why got positive value, positive V, and why got negative V leh? Well, if you think about the pendulum, right? let's say again, we stare at this pendulum, big, okay. This pendulum could be on the way down. It could be on the way up. We don't know, okay? So let's say I take the middle point here, which was where I draw on the graph right here. Sometimes the pendulum is to the left, negative V, to the right, positive V, to the left, negative V, to the right, positive V. So that's why you will have both positive and negative values, okay? So when the pendulum is swinging to the left, will be negative value. When it's swinging to the right, you get positive values. So I guess I'll highlight for you. So every point up here, the pendulum is moving right. Or it may not always be a pendulum. It can be a spring. It can be any kind of system. Or system moving to the right. By the way, right, all this right or left, positive, negative is set by you or set by the question one. So just this is why you have this two direction graph. Whereas everything that's in the negative portion here, this one, we can say that the system is moving, the motion is in the left direction. Okay, so that will be the interpretation of the graph. And you may be wondering, teacher, got equation this graph? Got. Let me show you how the equation looks like. Nah, this is the equation. But this equation is given during exam. Yay! I don't edit my videos, but I will insert the cheer sound. Okay, so this is the equation. Just know how to use the equation. That's all. You may be wondering, what is x naught? Well, x naught is amplitude because they use x naught. Look, it's up to you. You want to use capital A also can. I prefer capital A. But you could use x naught. So just for completion's sake in the notes, I will write something here where the equation of the line, this equation of V is equal to plus minus. Oh, that's why I got both positive, negative. Yes, correct. Okay, so plus minus square root of hang on, where did my omega go? Plus minus omega square root of x naught square minus x square. Okay, this one is important equation, but also thankfully it's equation that is given to you. Okay, this is the equation. All right, so at this point here, it's just good to remind ourselves that x naught also happens to be equal to A. Another thing about Vmax. Vmax happens when x is 0. Okay, so I'm going to just try to substitute what happens when x is equal to 0. So then your V will be equal to plus minus omega square root of, okay, let me zoom in a bit, plus minus omega square root of x naught square, or I guess I like a square, so I'm going to put a square, okay? A square minus 0 square. And then you see your AV is plus minus A omega, correct? So this Vmax here, up here will be A omega. And the other Vmax will be plus minus negative A omega. Okay, so what you need to know is the intersection points. Okay, how to sketch the graph, the intersection points. Okay, so for example, if I give you this graph, you should be able to find the maximum velocity either by inferring from the information from the question or reading the value on the graph. Okay, so if you know the intersection point, Vmax is A omega, and you know that it will cut, basically the velocity will be 0 at this point, then it's okay. And if you do some maths, you will be quite comfortable with this equation because this is the equation of an ellipse. Okay, so that's it. That's it for the velocity against position graph. So always think about this from the perspective of position. We want to be able to describe velocity in terms of position. Equation is given to you. The first equation, that one is with respect to time, and that is another video, not this one. All right, so this is what we've learned today. When we want to talk about kinematics of simple harmonic motion, we can look at the pendulum bob. The acceleration of the pendulum bob will change with position, and so does the velocity. Okay, one last part okay, which is we've done the kinematics. Now we need to look at the energy. So sometimes we use them interchangeably to describe a system, okay? But to make our lives easier, I will always consider kinetic energy together with velocity. So give me a second to copy the Vx graph over here. Okay, this is my little ellipse Vx graph. Okay, value here is amplitude, value here is negative amplitude. So I can transfer over here amplitude, negative amplitude, because I'm plotting a graph of energy against position. Okay, so right now, if I look at V is given by the equation V is equal to plus minus omega square root of a square minus x square. Okay, so right now up here, this value is a omega, and the bottom value is negative a omega. All right, your maximum value here and here. Okay, I think we're good to go. So let's think about kinetic energy. Of course, the kinetic energy will be maximum here. So I expect Ke to be maximum. Let me move the axis a little bit. Okay, graph of energy against position. We know that here is Vmax, this point here. So here should be maximum. So here, at this point here, should be Ke maximum. Where is Ke 0? When the particle is not moving, lor, teacher. Yeah, lor. So here, lor. Here, particle not moving. Here, particle not moving. So you're going to connect them together. Is it going to be a curve? Yeah, yes. Should I draw a straight line? No. But when you draw a curve, please make sure that it looks like a inverted quadratic curve. Okay? So the quadratic curve like this. Inverted, basically, it's a negative x square graph. So decreasing gradient until 0, increasing gradient. Okay, something like this. Now you may be thinking, teacher, this one got equation. Well, you see you have the equation for V. So now you want to find the equation of kinetic energy is easy. Okay, so to find kinetic energy, we will take half mv square. So we have the v square, right? To look at the equation here, I'm going to square the whole thing. Omega square a square minus x square. So from here, I will get half m omega square a square minus half m omega square x square. Now, my friends and family, I don't know whether you know this, but this whole thing is constant. The mass of the pendulum is constant, the period is constant, unless I change something about the pendulum, and the amplitude is also constant, so our body here is constant. You see this negative x square? That's why you get the negative x square shape, okay? Where this one is constant. So when your x is equal to 0, what happened to this term at the back? It disappears, right? So I can also double check when x is equal to 0, okay? Your kinetic energy will be equal to half m omega square a square. And some of you who are a little bit perceptive, you will notice that, teacher, need so complicated, meh? You see, the kinetic energy is half m, but this is a omega square. So this is actually half m maximum velocity square. I don't have to memorize a new equation. You are right. You don't have to. It's the same thing because you already know that the maximum velocity is a omega. Okay, so because of that, you will know that if you want to find the max Ke, this one here, maximum Ke will be half m a omega square. So I got value here, bro. Half m a omega square. Sorry, a square omega square. I think it's better to put the square in because sometimes transfer error is possible for everyone. All right, okay. So this is the kinetic energy graph. And you may be asking yourself, what about the potential energy? Well, you know, kinetic energy and potential energy are like BFF. Like one energy change and then it converts to the other energy. Let me show you a quick visual about that. Okay, so what I have behind me, it's a pendulum. Look at it, it's swinging, it's having a good time. So you will notice a few things. Let me slow motion this. Okay, let's look at the graph. Look at the graph here, okay? Hopefully it's not too small. So there are two graphs. The green graph is the kinetic energy. Now stare at the green graph. Where's the green graph the greatest? In the middle, equilibrium position. Green graph dropped to 0 at amplitude. Maximum at here, green graph dropped to 0. But hey, the blue graph is potential energy. You notice the potential energy will has an invert relationship with KE and PE. One will go up, one will come down, as according to conservation of energy. So from conservation of energy, I know that the total energy of this KE plus PE must always be the same. Total of the blue graph, okay, if I pause at any point at all, you see, this graph, kinetic energy plus potential energy will always be equal to the total energy. And even at the equilibrium position, let's say this is close enough to the equilibrium position and the kinetic energy is maximum, PE is 0, it's the same as the total energy. So pretty good. This thing is going to be the same all the time. And because there's no loss in energy, so it will just keep KE convert to PE, PE convert back to KE, and it will keep cycling on and on and on. Okay, so how would that look like for our position graph? Energy against position graph. Let's check it out. Okay, so here we're looking at the graph now, and I think I should label. Hang on. Always label your graph when you got more than one graph, okay? No label graph is a dangerous thing. Okay, so this is kinetic energy. So we know potential energy will have a inverted relationship, meaning when KE is increasing, let's say I grow from negative A to 0, KE is increasing, your PE will be decreasing. PE will drop. Give me a sec. PE will drop something like this, and then increase in the opposite direction like this. So this is PE. Teacher, the maximum value the same. Yeah lah, conservation of energy, my friend. So the potential energy and the kinetic energy, when you add these two graphs, you will always get the same value. What is the same value here? This one is total energy. Total energy, which is, I'll call this ET lah. ET is KE plus PE. Okay, so if you may be thinking, do I need to know equation for this? Not really, but if you really want to, you can derive it. It is possible. Okay, so this is what you need to know, be able to interpret the graph. So in this chapter, it's a lot of like either they ask you to sketch the graph or they give you a graph and they ask you to get information from the graph. It's a two-way thing. So it's either give info, you sketch graph. Give graph, you find info. Okay, so the interpretation of this graph is important. So when I take the blue graph plus the KE graph, I will get the green graph. Okay, and if you want to know how all of this looks like put together, let me show you something else. Okay, so we have done the graphs on the left side, this side for our video. Okay, so you can see this one all describes simple harmonic motion, which is pretty cool. Wherever I pause, let's say I pause here. I missed out. Let's say I pause here at equilibrium position. The displacement is 0. The particle is at this point. Okay, I don't know whether you can see. Maybe I should just make it bigger. Okay, the particle is at this point. Particle is here. Okay. Velocity is the fastest. Now, because it's on the way up, okay, this simple harmonic motion is up and down, not left and right. Because it is on the way up, so the velocity is positive. A is proportional to x, so the acceleration is 0. Okay. Kinetic energy is maximum, potential energy is 0. Pretty cool. Okay, let me continue. Let's say I look at maximum displacement here. Displacement is maximum, velocity is 0, but because it's on the way down, so it's on the negative side. Okay, acceleration is maximum. Okay, look at here. KE is minimum because velocity is minimum and potential energy is maximum. So if I carry on this thing, up and down, you will notice that it just shows you different description of this beautiful particle that is in simple harmonic motion. Okay, and this thing is pretty cool because you are talking about some consistent oscillatory movement that is prevalent or very often found in in the real world. You go look around your world a bit. Okay, I know if you're in lockdown pandemic, there's not many things to look around. But look at all the things that are oscillating in your life. So many, including your mood. Okay, just joking. Okay, so that's all. That's all for this video. We need to know how to interpret the graph, sketch the graph, and if possible, find the maximum and minimum values. That's it. Okay, you want to know the derivation for the velocity displacement video for the physics. You want to look at the graphs on the right, another video. Okay, that's it. Thank you for studying with me, and I'll see you in the next video. Bye-bye.